Good day. For those of you who do not know us, we're the instructional staff for ECE 150, professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to look at linked lists with tail pointers. Now, in this topic, we will describe how we can implement a tail pointer in the linked list class and describe its purpose. We will therefore update the constructor and the pushFront and popFront member functions to account for this new member variable. We will also implement the pushback and popback member functions using this new member variable. However, we will see that it is still a very expensive operation to pop the last node in the linked list. Consequently, we will consider solutions to deal with this last issue. Now, currently, as you may remember, it's quite easy to add a new node at the start or front of the linked list. All you do is create a new node, initialize it appropriately, and then set the list head pointer to store the address of that new node. Now, how about adding a new node at the back of the linked list? Well, to do this, we have to get to the last node because the last node is the one that we have to modify. So currently the last node has null pointer as its next node address. So if we want to add a new node at the end of the linked list, we have to create a new node and have what is currently the last node now store the address of our newly created node. So let's see how we would do that. Now, once again, the special case is when the linked list is empty, because then you have to update both list head and so in this case, if the list is empty, just call pushFront, because pushing at the back of the linked list is the same as pushing at the front of the linked list if the list is empty. So we've done the work once, no need to do it again. However, if there's at least one node in the linked list, let us start by having a pointer to the current back. We'll initialize this with the list head. Now we're going to have a simple while loop. So while the current back pointer, while its next node is not equal to null pointer, we're going to update current back to be the address of the next node in the linked list. So basically, we check the first node. Is its next pointer null? If yes, we're then at the last node. If not, we will update the current back to point to whatever it's pointing to. Then we'll check again. Is your next node pointer equal to null? If yes, now we're at the back. If not, we'll keep on going. Now we're guaranteed this will work because we checked if it was empty. So at this point, we're guaranteed that there is at least one node in the linked list. However, once this while loop finishes, the pointer to the current back local variable stores the address of the last node in the linked list. Thus, we can perform our critical code. We will update the next node of the current node at the back of the linked list by setting its next node to a new node that stores the new value we want, and its next pointer will now be null pointer. Also, we'll update the list size member variable. Now, this requires us to traverse the entire linked list. And if there's 50 or 100 things in that list, then this could take a while. Now, why might we want to add a new node at the back of a linked list? Well, consider using a linked list for a queue or lineup. Suppose your task is to store web requests while a single web server is processing those requests one at a time. Now, it may happen that one or more requests may come in while the web server is currently responding to one specific web request. What do we do with the other requests? Do we just say, sorry, we can't help you? Well, that would be suboptimal service. Instead, you're going to do exactly what a grocery store does or what a bank does. You will store those requests that are waiting in a queue. And like a store or a bank, you will then service those waiting requests one at a time as the web server becomes ready to serve the next web request. We could use a linked list as a queue. So whenever a new request comes in, we will push that new request to the back of the linked list. And whenever the web server is ready to satisfy the next request, we will pop the request at the front of the queue and then service that request. Now, our linked list is storing a double. So if you were to create a linked list in order to store web requests, it's going to have to store something a little bit more substantial than just one double. Now, how can we easily get to the last node in the linked list? Well, how about having a member variable pointer to list tail, which we always keep assigned to the address of the last node? So now our linked list class would look something like this. We have a pointer to the list head, pointer to the list tail, and a list size. So what's this going to look like? Well, now our linked list class will have two pointers. The first one is pointing to the first node, and the second is pointing to the last node in the linked list. Note again that there's no change to any of the other nodes in the linked list. This is simply a change to the linked list class, not the node class. Now, for the constructor, when a linked list is being created, its initial size is 0, so like list head, list tail will be initialized to the null pointer. Now we have to update some of the other member functions. Again, the ones that are modifying the linked list. So push front, for example, now has to update the tail pointer, but only if the linked list is empty. So here's our updated push front. We are going to, as before, update the pointer to the list head to store the address of a new node that is storing the new value, and the next pointer of which is the current value of the pointer to the list head. Now we will use list tail and check. If the pointer to the list tail is equal to null pointer, that means that prior to this call, the linked list was empty. Consequently, at this point and this point only do we assign the pointer to list tail the same value that is currently assigned to pointer to list head. Again, we updated list head first, then list tail, and then we update the list size. We've also got to update the pop front function. So as before, we stored the old head in a temporary variable. Then we updated the pointer to the list head by assigning it the next node address stored in the first node of the linked list as it currently exists. Now, when do we have to update the tail pointer? We have to update the tail pointer if the linked list is now empty, because otherwise the tail pointer is always storing the address of the last node in the linked list. And so the only time that will change is if the node that is being popped is also the last node. Well, we know that the node that is being popped is the last node if list head is now assigned null pointer. So if list head is assigned null pointer after updating it, then we have to also set list tail to be the null pointer. We then decrement the list size and delete the old list head. Now, here's something that I would suggest you not do. In this case, in the last example, we updated list head, and then we checked the updated value of list head. This piece of code is relying on the fact that the size variable has not yet been changed. So that looks a little bit awkward because it's saying if the size is 1, then set the tail pointer to null pointer. But that's only being done because we know that list size is being decremented after this step. So that looks a little bit fishy. I personally prefer the previous implementation where we updated list head and then checked the new value of list head to determine if we have to update list tail. And as before, we can also implement a back member function that returns the value stored in the last node of the linked list. This, of course, requires that the linked list is not empty. So how do we add a new node at the back of this linked list? Currently, the last node in this linked list is pointing to null pointer. If we want to add a new node at the back of the linked list, we have to update the next pointer of that last node so it stores the address of a new node that we've created and initialized. Now, the new node we just created, it now has a next pointer that is equal to the null pointer. Also, at this point, we then have to go and update the tail pointer so it is now storing the address of the new tail of the linked list. Implementing this in code, our pushback function will, as before, if the linked list is empty, just call pushFront, since we've already dealt with the special cases there. So to push at the back otherwise, what we will do is we will update the current tail of the linked list's next node to be assigned the address of a new node that we have created that is storing the new value and that has null pointer as its next node address. So now the linked list is correct, but we still have to update the tail pointer. So the tail pointer will be updated to store the address of what the tail pointer was pointing to, its next address, which we just updated. All right, and then of course we can increment the list size and we are done. Implementing this in code, our pushback function will, as before, if the linked list is empty, just call pushFront, since we've already dealt with the special cases there. So to push at the back otherwise, what we will do is we will update the current tail of the linked list's next node to be assigned the address of a new node that we have created that is storing the new value and that has null pointer as its next node address. So now the linked list is correct, but we still have to update the tail pointer. So the tail pointer will be updated to store the address of what the tail pointer was pointing to, its next address, which we just updated. All right, and then of course we can increment the list size, and we are done. Now, how could we pop the last node in this particular linked list? Well, what we could do is update the tail pointer to move the tail pointer to the second last object, or the second last node. Then we could free the last node or delete it, and then update what used to be the second last node to have it point to null pointer. All right, that's reasonable, but how do we update the list tail? Now, popping at the back is a little bit more complex. First of all, if the size is 1, popping at the back is the same as popping at the front. So we're just going to call pop front in that case. If the size is not 1 and the linked list is not empty, that means there are at least 2 nodes in the linked list. So what we must do at this point is find the second last node. And again, it's important that there are at least 2 nodes in the linked list, otherwise the code may not work. So to get to the second last node, I'm going to designate a new local variable pointer to new tail, which is initialized to the pointer to the list head. Now, so long as the next pointer of the new tail is not equal to the current tail pointer, I'm going to step the new tail through the linked list. This will keep on going until new tail is storing the address of the second last node in the linked list. For once we get to that point, its next node address will be the same as the list tail address. All right, so now we have to perform our critical code where we are updating the member variables of the linked list class. First, I'm going to make a comment that there's no need to update the pointer to the list head because the size is greater than 1. Next, I will update tail pointer to store the address of the second last node in the linked list, which we just found. I will then call delete on whatever is the next node of the second last node in the linked list. I will then set the next node of what is now going to be the last node in the linked list, the value of null pointer. And finally, I will decrement the list size. All right, so we have now deleted the last node in the linked list. Nice. Now, popping the last node requires us to access that second last node. Finding the second last node required us to walk through all of the nodes in the linked list. Now, for very large node lists, that could actually be a very expensive operation because we have to step through the entire linked list. Fortunately, this is not required if you are using a linked list for a queue. And in fact, a lot, if not all operating systems, make significant use of such queues throughout the services provided by the operating system. Why is this? Because for a queue, when a new request comes in for a service, we push that request to the back of the linked list. And we can put a new node at the back of a linked list very quickly with only a few assignments and initializations. When we are ready to service a request, be it in the bank, a grocery store, or in the operating system, we pop from the queue that request that has been in the queue the longest, and that is the request that is currently at the front of the queue. And once again, we saw that it is very fast to pop the node that is at the front of a linked list. Nevertheless, in some applications, you may be required to pop the last node efficiently. By efficient, I mean not walking through the entire linked list. We cannot add, for example, another member variable that points to the second last node, because once we pop the last node, then we have to have the second last node pointer pointing to what used to be the third last node, and that once again requires us to walk through the entire linked list. So that's not going to work. Instead, we must change the node class itself. The node class must not only store the address of the next node in the linked list, but it must also store the address of the previous node. What that means is that if a node is in the first location, then its previous pointer is going to be null pointer. However, if it is at the back of the queue, it will have to be assigned the address of the second last node in the queue. Now, this is something some of you might try implementing yourself for fun. So, following this topic, you now know how to implement a tail pointer for a linked list class. You understand how to update the existing member functions of pushFront and pushBack to correctly update for such a tail pointer. You also know how to implement a pushBack member function that is reasonably efficient. However, you also understand how to implement a popBack member function with the knowledge that this is actually potentially a very expensive operation if the linked list is too large. You are aware that a linked list could have nodes with two pointers, that is, one that stores the address of the next node in the linked list, and a second pointer that stores the address of the previous node. Here are the references, the colophon, and a disclaimer. Cheers!